Math 2414, area between curves. Area between curves, example 1. You'll notice that I've summarized the main idea from the previous video here. Find the area of the lamina bounded by the graphs of y equals e to the x, y equals x, x equals 0, and x equals 1. Just a reminder, lamina is just a fancy name for a flat surface. It might have some more requirements like being connected and bounded, but for now it's just a flat surface. Alright, so find the area of the lamina bounded by the graph. So we're finding the area between, well, first off we should know what this lamina looks like. So let's sketch this, and it's always a good idea to sketch the picture of the thing that you're finding the area of, because you have to check to make sure that one graph's function is above the other graph's function. Alright, so how are we going to do this? Well, let's start with y equals e to the x, which you should know is an exponential function that starts low, asymptotically on the left side of the x-axis, has an a y-intercept of 1, and then proceeds to grow exponentially. So there's y equals e to the x. The graph of y equals x is what I call the perfect diagonal line. It goes through the origin and bisects quadrants 1 and 3 at a 45-degree angle. Or it's a line with slope 1 and y-intercept 0. So it goes through the origin, and a slope of 1 is a perfect diagonal. So it looks like that. So here's y equals x. And it's important to know which graph is above the other so that you set up the subtraction problem in the correct order. If you set it up in the reverse order, your answer will come out negative, at which point you just say, oops, other way around, and change the answer to positive. There's an exception to that rule, which we'll run across. Oh, but what about x equals 0 and x equals 1? Well, those are just vertical lines. And in retrospect, I wish I had drawn the first two graphs in a different color, so I'm just going to erase them real quick and draw them in another color. You don't have to if you're taking notes. And if you're not taking notes and you're in my class, then why are you not taking notes? Okay. Graphs are more fun if you give sound effects. Alright, so there's y equals x. Alright, so what about the graphs of x equals 1 and x equals 0? Those are just vertical lines. X equals 0 is a fancy name for the y-axis. So there's the graph of x equals 0. And then x equals 1 is just the vertical line that goes through, well, x equals 1. So there's x equals 1 and the vertical line that goes through it. Do you see the lamina that we're finding the area of? It's the lamina bounded by the graphs. And by the way, the word bounded has a specific meaning. I think I mentioned this in a previous video, but a lamina is bounded if it can fit inside of a circle of finite radius. For example, this lamina here is unbounded because it goes forever. There's no finite radius circle that will fit inside of. The only bounded lamina is here. If you're thinking, well, what about this triangle that's bounded? Well, it is, but it's not, because the x-axis is not serving as one of our boundaries, so we can just kind of erase that. It's not really there. So it is the only bounded lamina bounded by all four of these graphs. All right, so now we know who's on top. The one on top is the e to the x. The one on the bottom is y equals x. And so now finding the area is just a matter of setting up and executing the integral. The area that we're looking for is the integral over, well, the x-axis is gone, so I'll restore it. The left end of this is at x equals 0, and the right end is at x equals 1, which is explicitly given to us, won't always be the case. But we're integrating from 0 to 1, the top minus the bottom. The top is e to the x, the bottom is x. So we just have to find the integral from 0 to 1 of e to the x minus x. And for those of you who just took my test over integration techniques, you should be looking at this and going, thank goodness, an easy integral. The integral of e to the x is e to the x minus the integral of x is 1/2 x squared. This is getting evaluated from 0 to 1. Now, some of you are in the bad habit of ignoring the 0. Don't. Sometimes it's ignorable, sometimes it's not. The safest thing to do, play it all out. Put in 1 for the x, e to the first, minus 1/2 times 1 squared, minus, put in 0 for the x, e to the 0, minus 1/2 times 0 squared, And some of you might be thinking, do I really have to show this step? And the answer is, it's not a bad idea, because if something goes wrong, I can give you partial credit because you're telling me that you know what this means. If something goes wrong and this isn't here, I can't give you credit for that move. You want to give me as much as possible to give you partial credit in case something goes wrong. Let's continue. E to the first is E. 1/2 times 1 squared is 1. So that's the first parentheses, minus. E to the 0 is 1. And then minus 1/2 times 0 squared is minus 0. And the reason I said it like that is because I can't just ignore the 0 as a lower limit of integration because it doesn't annihilate this antiderivative. In other words, this doesn't disappear when I put in 0. There's still a 1 there. So let's see what we can put together. We have an E, we have a minus 1/2 and a minus 1, and if you combine those, you get minus 3/2. To me, this is a perfectly acceptable answer, but for those of you who insist on trying to do the subtraction, because it's a subtraction of fractions, you could drop a 2 on both sides of the fraction here, and you could write 2e minus 3 over 2. Which answer is better? I don't know. I think the first one's better. I think the second move is just kind of pretentious, but hey, who am I to judge? So yeah, finding the area between two curves is just doing the integral of the difference of the top minus the bottom over the correct interval of x values. So what could possibly go wrong?